So Henry's law governs the solubility of a gas in a liquid. And so that's a situation where usually in the liquid, because the particles are able to form attractions, they come close together. So it might be water, and the water molecules have some hydrogen bonds, or whatever the solvent is, there are going to be some type of attractions between the solvent molecules. If it's a liquid at a given temperature, the attractions are probably significant enough to hold the particles close together. So if you have a sample of a gas over top of that, and whatever the gas is made up of, usually the atoms or molecules in the gas phase don't form very good attractions. Right? If those atoms or molecules were highly polar and able to form nice, strong intermolecular attractions with one another, they probably wouldn't be a gas to begin with. They'd probably glob together as a liquid or a solid. So Henry's law basically just says that if you have more pressure of the gas on the surface of the liquid, then you will have a greater concentration of gas dissolved. So because these particles of the gas are usually low or non-polar, they don't usually have much polarity, they don't usually form strong attractions with the sample of the liquid. Right? So gases are not very soluble in liquids like water. If you heat up a sample of water, initially the bubbles you see forming are not water boiling. You'll see bubbles forming inside the water before it gets to the boiling point usually. That's the small amount of gas that's actually dissolved in the water, right? Because in the atmosphere there's nitrogen and oxygen and other gases, and when they're moving around in space, sometimes they happen to be moving in a direction that plunges them into the surface of the liquid. Once they enter the surface of the liquid and break some of these hydrogen bonds, whatever that gas particle is, maybe it's a molecule of nitrogen, it's going to probably form some induced polarity. So maybe the electrons shift to one side and create some temporary partial charges. Right, so this will be, some of this will form these attractions and stay in here for a little while, but if this is a fast-moving particle and it can overcome these attractions, it'll just go back out and become a gas again. So eventually you reach an equilibrium where the rate at which some of these gas particles are entering the solution is the same as the rate at which some of the particles are leaving the solution. The slowest moving ones, when they come in contact with the liquid, can start to form these attractions. The fastest moving ones that have already formed attractions can break those attractions and escape. So if you want to know how much of these are actually going to be in the liquid dissolved, Henry's law says that that depends upon how many collisions there are between the gas and the liquid. The more of those I have, the more particles of gas I'll have dissolved in that liquid when it gets to that equilibrium that I reach. So I can create more collisions by putting more of the gas above the liquid, which would create more pressure. So basically that says that I can increase the concentration of the gas. So we use these brackets to indicate moles per liter, or molarity, or concentration. I can increase that by increasing the moles of gas above the liquid. I can increase it by decreasing the volume of gas above the liquid. That would force the particles into a situation where they'd be colliding with the surface of the liquid more because they have less space to spread out in. Those two would, either one of those would cause an increase in pressure of the gas. So that's really what Henry's law says, is that if you have a greater pressure of the gas, you have a greater amount of gas dissolved in the liquid. We didn't really talk about the effect of temperature, so I probably won't ask you that. We can just mention it real quick here. The amount of gas dissolved in the liquid depends on a couple things. It depends on how often the gas particles are going to come in here and collide with enough energy to break the hydrogen bonds between the water and insert them into the liquid. It also depends upon, once they get in there, if they form attractions, are those attractions going to be able to hold them in the liquid, or are they going to be weak, and is the gas going to then escape the liquid and go back into the gas state? So the moles of gas and the volume of the gas affect one part of that. They affect the part where we're thinking about how often the gas is going to enter the liquid. The other part, which is how often is the gas leaving the liquid, that's mainly affected by temperature. So if I increase the temperature, I will decrease the concentration of the gas dissolved in solution. Right, so temperature change, increasing the temperature will increase the pressure of the gas, but the larger effect it will have on the solution is, if I increase the temperature, it makes the particles move around faster, so it's harder for them to maintain attractions, especially the weakest ones. And so the majority of the gas will be moving fast enough to break any intermolecular attractions that form into the liquid, and that will cause it to leave at a faster rate than it enters, and so I'll have less gas dissolved when the equilibrium is reached. Questions about that? It's all about the intermolecular attractions, man. Other questions?
Are we going to be discussing potential kinetic energy in further detail today?
Yeah. Yeah, we're not going to talk as much about kinetic energy, but they are kind of related, and we're going to talk about both of them in the context of chemical reactions, right? So we talked about that a lot in the context of phase changes, right? So if you want to melt a solid, or if you want to freeze a liquid, or if you want to cause a solid to undergo sublimation, what has to happen is you've got to, in order to undergo a phase change, you've got to break some intermolecular attractions or form some intermolecular attractions. And anytime you're breaking or forming attractions, there's going to be a change in potential energy, right? Because if the attractions are held tightly and they're strong attractions, it's a low potential energy state. If I want to break those, I have to put energy in to increase the potential energy. And then if I form attractions, energy is released into the surroundings. So anytime I'm forming or breaking attractions, I release or absorb potential energy. And that energy has to come from the surroundings in the form of usually kinetic energy. Could come from the in the form of light energy or electrical energy or something like that, but the simplest cases we'll be talking about are where it comes from kinetic energy. So you can see the kinetic energy of the surroundings going up or down depending on whether it's absorbing energy from the system or putting energy in the system to break those attractions. And that will cause the surroundings to have a temperature change. So those things are not just relevant to phase changes, but also to situations where you actually do a chemical reaction. You actually break covalent bonds or rearrange the electrons.